Hello everyone, welcome back. Today we have Nathan Reading and he's going to talk about some structural questions about cluster algebras. Thank you, Nathan.
Thank you very much. I appreciate the invitation and I'm very grateful to the organizers, not only of the seminar, but of the entire program and all the workshops, because despite not being able to travel to England, I've been really enjoying and learning a lot. So thank you. I think this might be my second actual talk given from my office. So I've thought somewhat nervously about what I do if someone knocks on my door and won't go away, or if the phone rings, or if somebody pulls the fire alarm to get out of an exam, but we'll deal with those as they come. I also realized that my title and abstract, once I had submitted them, I realized they're rather vague. So hopefully by the end of the talk, I will you'll have an idea what I'm talking about. And so thank you for being brave enough to come, despite the vagueness of the title and abstract. But the purpose of this talk is to pose some structural questions and problems related to matrix mutation and cluster algebras. You'll see what they are, and ask you to consider what they mean and how they might be approached in your world. So I will talk about some results that I have and some results that other people have, but I think my main purpose is really to ask you to think, because when we go to a cluster algebras conference, I know that this is, this has representation theory in the title, and that's not my strongest point as a cluster algebra person, but we have lots of people covering lots of different directions. And so my thought is, let's think about whether some of these things mean something in the world where you come from. And let me just define that term, your world. I mean, the techniques, constructions, and tools that you use for your research and or the settings where you might be applying ideas from cluster algebras. So also this is somewhat older research in some ways, not the very newest things I've been thinking about, but I think some of this, I think very few of you have heard about, and some of it, maybe some of you have heard about. So let me get on with it. Let me start with an introductory problem. I'm going to use notation from cluster algebras 4. So let me just quickly review. You have this bold T sub n, it's the infinite n regular tree. You're labeling every edge 1 through n so that every vertex has each label. And so you can use that as a scaffold on which to build a cluster algebra or a cluster pattern. So B sub T is an exchange pattern. Every vertex T of the tree has an exchange matrix B sub T. And if you look at two vertices connected by an edge labeled I, then those matrices should be related by mutation along I. We're going to assume that there are no 0 rows columns in B. And I'm going to use this notation, which is also from cluster algebras 4, where G sub, and you can sort of let your eyes glaze over this notation in some sense, but at the top and in the superscript, you have an initial exchange matrix at an initial location in the tree. And at the bottom, you have another location, T prime in the tree. So T prime is a vertex in the tree. And I actually just realized I left that out. So this is the G vector of the ith cluster variable in the seed at T prime, which doesn't appear on the slide. And then the B and the T are showing that there's initial matrix B at T. So here's the problem. So suppose I have, and I think this, especially right now, is the place to let your eyes glaze over the notation. Suppose I have just a bunch of distinct G vectors. I fixed an initial exchange matrix, and I have a bunch of G vectors in that come from the cluster pattern. Okay, and I have some integers, positive and negative, and I want to suppose that the linear combination of these G vectors is 0. But not only that the linear combination of these G vectors is 0, but also, and if you look at where things show up in the notation, I want to say for all T's. So in other words, if I do initial seed mutations, or if I change the initial seed for which I'm calculating G vectors, I want this relation to still hold. Okay, so it's a linear relation among G vectors that holds no matter what initial seed I calculate G vectors for, or with respect to, I should say. I'm going to prove that all these CJs have to actually be 0 for this to work. Okay, so let me clarify what I mean by hard. Hard is that I have no idea how to do this in general. There's some cases I know. Now, my definition of hard might overlap with your definition of easy on this problem. It might be that you know some way to do this, or maybe you have machinery that does this, or maybe you see something that I don't see how to just do it just straight from the structural setup. And that's part of the reason I'm giving this talk. So the question is, does this problem mean something in your world? And then we're going to let this be an introduction to a problem that's related, and that this will be somehow a special case of. So just this is just the same problem on the board with a little less wordy, so we can keep talking about it. I want to tell you what a mutation map is. I think this came up in Pavel's talk, but not with this notation. So I want to say eta superscript k. So I've got this bold k, and the bold k is a sequence of indices. So this is a sequence at which one might mutate, right? And superscript b in the notation for this mutation map, and that's just saying what my initial exchange matrix is. And what I'm going to do is I'm going to take a real vector a and make it a new last row. I'm going to put it below b, and then I'm going to mutate that sequence. And then I'll read off the last row that I get from mutating that sequence, right? So real vector in, put it at the bottom of the exchange matrix, mutate according to whatever the bold k is, and then the answer, read off the answer, whatever that row became, whatever that one coefficient row became. So the theorem, and this is a rephrasing in this language of mutation maps, but it's really Fomin, Zelevinsky, Nakanishi, Zelevinsky, and then GHKK, is that this mutation map does initial seed, is the initial seed recursion for G vectors. Okay, so it was conjectured by Fomin and Zelevinsky. Nakanishi and Zelevinsky showed that it was equivalent to sign coherence of C vectors, and then GHKK, Gross, and Kulik-Savage, showed that it actually proved sign coherence of C vectors. So that's the theorem, and so let's use that to phrase our problem. So the problem is to prove that there's no non-trivial linear relation among G vectors of cluster variables that remains true when the G vectors are individually and simultaneously subjected to mutation maps. Okay, so I have all these G vectors. I take each vector, apply the mutation map. I'm not applying it to the sum, right? I'm applying it inside the sum and inside the scalar multiplication. And then I want to see that, in fact, if I have a linear relation that holds no matter what mutation map I apply, that actually had to be trivial. Okay, so this is essentially conjecture 8.23 of a paper of mine, and I want to explain what I mean by essentially. Essentially means modulo really terrible typos that I only found within the last few weeks as I was preparing this talk. And you know, there's typos and there's typos. Sometimes typos look bad and are embarrassing, but sometimes typos, you look at them and you think, people don't know what I'm trying to say, they really won't get it. So it's unfortunately those kinds of typos. So at least on these slides, it'll be correct. So any questions about the problem?
I'm sorry, Matt.
Yes.
Could you please repeat the problem again? I'm sorry for being slow and stupid, but I kind of...
No. The problem is, we can phrase it in two different ways. One is that I have, so one's at the top of this slide. I have a bunch of G vectors. I've just chosen some cluster variables, basically, right? And I'm going to compute their G vectors with respect to some seed, some initial seed. And then I want to write a linear combination of those G vectors and get 0. But I want that linear combination with the same seeds, with the same, the same integers in front of the G vectors. I want that to hold no matter what initial seed I'm calculating G vectors with respect to.
Okay, I got it.
Okay, and then the rephrase is that actually this is asking for that that linear combination to hold up if I apply these mutation maps. In other words, apply the maps that Fomin and Zelevinsky gave for initial seed mutation of G vectors to all those vectors.
I have a really stupid question maybe, but are these cluster variables that you are having compatible or not necessarily? You are taking any...
Not necessarily
compatible.
I see. If they're compatible, I think we can prove that it's...
Yeah, okay.
Yeah.
Yeah.
Right. Yeah, so they're all over the place. Right. Other questions? Okay, feel free to interrupt with questions later. And I should say, by the way, I will be studiously ignoring the chat during this talk. So if you have questions you'd like to ask the audience during the chat, it won't disturb me at all. I like to do that, except I sometimes worry that I'm interrupting the speaker. You won't be. So let's talk about cluster algebras of geometric type, and I want to put this problem into a broader framework. So if you know cluster algebra is geometric type from cluster algebras 4, that's all this is. We're going to take our exchange matrix, we're going to extend it. We're going to have columns indexed by, just 1 through n, rows indexed by 1 through n. So the top of the matrix is just our exchange matrix B. And then the next rows are indexed by some indexing set, and we'll call those coefficient rows. We have some formal symbols, which we'll call tropical variables. We have a tropical semifield. The semifield structure will not be very important in this talk. If that bothers you, don't worry about it. Just, we're just, writing products of these formal symbols. And then from this extended exchange matrix, you can read coefficients. This is just the product of the, the tropical variables with with exponents given by the entries in the coefficient rows. And then a cluster algebra of geometric type is just, we're taking an initial cluster, we're taking the B matrix, and we're taking these coefficients, these Y's. And then there's a way to think about all this in terms of, mutation of the extended exchange matrix, et cetera. But I want to say broadly defined. So this is the part that's a little different from cluster algebras 4. So what does broadly defined means? By broadly defined, I want to give myself more freedom than cluster algebras 4 did. The entries of the matrix ought to be, the entries of the exchange matrix ought to be integers. Although, I've now listened to a few talks from Pavel and Anna. Maybe we should not be insisting on the entries of B being integers. But for me, I'm going to do that. The other entries of the extended exchange matrix can be in some other ring. And you don't need to worry so much about the ring. I want it to contain the integers and be contained in the real numbers. And there's sort of a reason that it seems to make sense to give ourselves that freedom. But usually we'll be talking about integers or maybe rationals or reals. And then the other thing that's very different is I'm not putting any requirement on the cardinality of the indexing set. In other words, I could have, if I want uncountably many coefficient rows, they're just indexed by some set. I think probably everything I'd ever want to do really, I want at most countably many, but I certainly want infinitely many. So the coefficient rows they're just a set of vectors in R to the n, which is not necessarily reals to the n, but some ring to the n. Okay, so now we got to talk about coefficient specialization. Coefficient specialization, we're going to start with extended exchange matrices. And again, if you know coefficient specialization from cluster algebras 4, this is a version of the same thing. We have 2 extended exchange matrices with the same underlying exchange matrix. And a coefficient specialization is a ring. There's going to be one more bullet point. I don't know why I hit it to start out, but there's going to be a coefficient specialization. It's a ring homomorphism from the cluster algebra for one extended exchange matrix to the cluster algebra for the other. And we want it to send initial cluster variables to initial cluster variables. And we want to send coefficients to coefficients at every seed. Okay, so it needs to, as you mutate, the coefficients change. We want to make sure that this ring homomorphism actually takes coefficients to coefficients to the corresponding coefficients in every other seed. And then the same, we need these coefficients with the auxiliary addition +1. And I'm just about to tell you that you can ignore that. So we're going to assume that B has no 0 rows or 0 columns. And if we assume that, then we don't have to worry about this auxiliary addition at all. But this thing about 0 rows and columns is kind of a tricky thing. I once had to write in a paper a little remark that sort of corrected another paper. It's, well, actually that result can go wrong if you allow 0 rows and columns, but it's, the basic idea is perfect. And, just there's this one little detail that happens. And then in the very next paper that I wrote, I made the same mistake. So it's a little tricky. You have to be careful of a special case with 0 rows and columns when you want to do coefficient specialization. But in any case, we all also want this ring homomorphism to restrict to a continuous R linear map on tropical semifields. And this is also maybe something that you can just, let be, a way of saying that nothing really bad happens. So let me tell you what I mean by that. So first of all, this tropical semifield we can think of as a vector space, or as a module, I suppose, over our ring, just a free module. So like a vector space indexed with the basis indexed by the i's, I guess. And the continuity is in the product topology of a bunch of discrete topologies. And that's just there to be official. What that does is it rules out a huge infinity of really stupid specializations. When I was a young boy learning linear algebra at my mother's knee, she taught me these things. She said, son, I just want to tell you, I'm not going to tell you about infinite dimensional vector spaces, but I want to tell you that if you ever meet an infinite dimensional vector space, Be very careful because it doesn't behave like a finite dimensional vector space. And so that's all this is. This is just so that we don't have to worry about crazy things that happen with infinite dimensional vector spaces. So that's what a coefficient specialization is. And this slide is almost the same. It's got a less long-winded version of the definition. I want to focus for a moment on sending coefficients to coefficients at every seed. What that means, especially if you put in the auxiliary addition with one thing that we are ignoring, that means that we're also going to send exchange relations to exchange relations, and therefore this map will have to send cluster variables to cluster variables at every seed. Now, if I was sitting in the audience, I wouldn't think that through that fast enough, so don't worry. But this is a property of coefficient specialization, so that they send cluster variables to cluster variables at every seed. But if we want to make one, we don't need that. We just need to just worry about the coefficients. So what we need is an R linear map that sends coefficients to coefficients at every seed. That's what we need to do to construct a coefficient specialization. I think this is really screaming out for an example now. So let's do an example. So here's a simple example. I have matrices that are written in black and matrices that are written in red. And there's going to be a coefficient, and the ones that are in red have some primes on them. But there's going to be a coefficient specialization from the unprimed matrices in black to the primed matrices in red. And it's shown here. So if I take the tropical variable u1 and map it to u1 prime squared, and similarly u2 will map to u2 prime, u3 will map to u1 prime, u2 prime, then what do I have to check that this is a coefficient specialization? Well, I'm checking that it sends coefficients to coefficients. So right here, my coefficient in the left column right there is u1 to the minus 1, u2, right? Reading down these and letting those be the exponents of my u's. And that's going to map to, it needs to map to u1 prime to the minus 2, u2 prime. And you see that it does. Right? And similarly, the same thing has to happen in the second column. So I need u2 to the minus 2, u3 to the minus 1. I need that to map to u1 prime to the minus 1, u2 prime to the minus 3. And you'll see that that also works. Now, if you think about what we're actually checking, and we also need to check that, we've checked that at this seed, but we need to check that it happens to coefficients at every seed. Okay, I'm not going to make you watch me write all those down, right? But if you think about what we're doing when we check that, we're really checking that if I index, these as like, in coefficient row 1, 2, and 3, and coefficient row 1 and 2, that we actually have a linear map. So I want 2 times the black first row plus the black third row to be the prime, the red first row. And I want the sum of the second and third rows in the black matrices to be, again, all these coefficient rows. So we're ignoring the top 2 when I number it this way. But the second and third coefficient rows should add up to the second coefficient row on the right in the red. And if you check, you don't need to do it now, but if you want, the slides I think were in the chat. So you can check if you'd like. This works, and it works for all 6. So this is like a linear relation among these rows that holds up when we mutate. So coefficient specialization means that coefficient rows of B prime tilde are linear combinations of coefficient rows of B prime, but they're persisting under mutation. Those linear combinations are persisting under mutation. So let's talk then, with this in mind, let's talk about what universal geometric coefficients really are. You're going to fix an exchange matrix B and a ring R that's in between, again, in between integers and reals. The universal geometric cluster algebra should be a universal object in the category of geometric cluster algebras with exchange matrix B. So we have category, in this whole category, we have B as the exchange matrix, the initial exchange matrix. But we're going to talk about the universal object. We're going to talk about an object that's universal in this category where the morphisms are coefficient specialization. So objects are geometric cluster algebras with exchange matrix B. Morphisms are coefficient specializations. Universal geometric cluster algebra is just a universal object in that category. So every geometric cluster algebra is a unique specialization of the universal one. And now if we think about the previous example where it's really just linear combinations of rows, so we want to find an extended exchange matrix B tilde, such that any other extended exchange matrix with the same B, that there's a unique way to write each coefficient row of this new extended exchange matrix B tilde prime, as a finite linear combination of coefficient rows of B tilde, and these linear combinations need to persist under mutation. So the coefficient rows of this universal B tilde are called universal geometric coefficients, just as a matter of terminology. Okay. So what we see from the previous example, really, as it is applying, as we've rephrased, coefficient specializations and universal coefficients, they're forcing us to think about something that you might call mutation linear algebra. This would be the study of linear relations that persist under mutation in the way that has happened in these examples so far. So what would mutation linear algebra be? So the basic idea is that we have this R to the n, and we have linear relations, but we're just declaring that only some of them are the good ones. Some of them are not. So a finite formal sum, sum of, coefficient times vector, sum of the CI-VIs, we'll call that a B-coherent linear relation. If first of all, when you evaluate it, it does evaluate to the zero vector, but also if it evaluates to the zero vector, no matter what mutation map you apply inside to each vector. Okay, so it's very similar to what we had with the G vectors problem. And it's also the same thing that's happening when we want to do coefficient specializations that we saw in the example. And again, if B has a zero row and column, then we have to think a little bit differently, but we won't here. Okay, so that's what a B coherent linear relation is. And then you can think of linear algebra as the study of linear relations on a vector space, maybe even on a module, right? So we are going to think of mutation linear algebra as the study of B coherent linear relations. And we'll use this notation R to the B, and it really just stands for R to the N. So it's really just, tuples of numbers, but the superscript B is telling us that we want to consider B coherent linear relations. So that's sort of the mutation linear structure of R to the B. So, what's a linear map? A linear map is a map that takes linear relations to linear relations. We don't usually say it that way because it's longer, but that's what a linear map is. And so a mutation linear map should be a map such that for every B coherent linear relation in your starting vector space, I'm going to keep saying vector space. I know that when R is not the real numbers, it's a module, or when it's not a field. But you start with a B coherent linear relation in your one vector space and apply the map to every vector, you should get a B coherent linear relation in your new vector space. Okay, that's what a mutation linear map should be. An independent set should be a set that admits no non-trivial B coherent linear relation. A spanning set should be, you can write a vector as a linear combination of other vectors, and that's a linear relation, that expression. So every vector in your vector space should have a, you should be able to write a B coherent expression that expresses it as a linear combination of vectors in the spanning set. And a basis is just something that's linear, that's independent and spanning. And that's our key concept, this basis. So if you want universal geometric coefficients for B, you want a basis for R to the B. And think about that example of coefficient specializations where it's really about these linear maps between coefficient rows, from coefficient rows to coefficient rows, but they have to survive when you do mutations. Now, this is something that's not like ordinary linear algebra. So I just wanted to throw in this idea that there's also a notion of a positive basis. And this actually comes up quite a bit when we're doing geometric coefficients. So A basis, it's independent and it spans, but a positive basis is independent, but also it spans sort of positively. So every vector in your vector space is a B-coherent, non-negative linear combination of vectors in the spanning set. Of course, you can't do that with ordinary bases of ordinary vector spaces, but so this is just something, I suppose it occurs in this talk really as a curiosity more than anything else. But so let me go to the question of when do universal geometric coefficients exist, but I'm going to answer that question as when do bases exist, and also mention when they're positive. So if R is a field, then there's this Zorn's lemma proof that every vector space has a basis, and you can do that. Just use the words differently. You say be coherent, and it just works. If your initial B is a finite type, then actually back to the cluster algebras 4 paper, Fomin and Zolovinsky proved, well, they gave universal coefficients in a larger category because they were not taking geometric cluster algebras. They were just taking cluster algebras associated to a matrix B, but theirs also provides a basis, in other words, universal geometric coefficients. In rank 2, this works. It can't always be a positive basis in rank 2, and if we have time, I'll show you that. It's conjectured to exist for affine type, and it would be positive no matter what, what ring you work over. That's in progress with Stella. Hopefully, eventually we'll get that done also. And there's a short list of surfaces and orbifolds where you can get a positive basis if you do the usual integers or the rational numbers. And the orbifolds cases are due to my former student Shirabio. Just to give you an idea sort of to what extent this is known. Another thing to say is that there does not exist a case where we know, there's a double negative here intentionally, there does not exist a case where universal coefficients are known to not exist. So it's possible that there are always universal coefficients. There also does not exist a case where positive universal coefficients using the ring R, the real numbers, there's no case where those are not known to exist, known to not exist also. Okay, so it's possible that if you're willing to work over the real numbers, you always have positive universal coefficients. And then I want to just tie this back to the introductory problem. If a positive basis exists for R to the B, then up to scaling, it contains the G vectors. Okay, there's a transpose, the G vectors for B transpose. And so the corollary is if you found a positive basis for R to the B, and really R could be anything, and this will work, the G vectors of B to the T are independent in this, sorry, B transpose. The G vectors of B transpose are independent in this mutation linear sense. And that would be exactly saying that a positive basis for R to the B gives a solution to our introductory problem, the one about the G vectors and having a linear combination of G vectors that holds up under all initial seed mutations. So I want to ask a question about your world now. What do coefficient specializations mean in your world? And I guess if we had more time and if this were really like an interactive class or something, I'd ask you to tell me. But in general, they're an algebraic way of changing coordinates. And I want to just emphasize this algebraic word because by algebraic, I mean, it's using a morphism. So there's also this separation of additions formula in cluster algebras 4, which says, you can take principal coefficients and then you do this auxiliary addition, and that lets you get, you change coefficients as you like. This is an algebraic way of doing it. In other words, biomorphism. The separation of addition sort of amounts to clearing denominators, and it's not biomorphism. But going on, what are universal geometric cluster algebras in your world? What does it mean? I know I've seen it talked very recently that you've also seen about universal cluster algebras in finite type. So is there something to be done further on? It just means that it's universal in the category of geometric cluster algebras, but maybe a better question for some of you might be, what are universal geometric coefficients in your world? So this is some really nice collection of vectors. They live wherever G vectors live in your world. I don't know if they're, vectors that you get out of modules or out of, subcategories or something. But wherever G vectors live in your world, there's this larger set that might be important. And, For example, does that larger set of G vectors, do they correspond to a family of modules that's important in general? Again, this is me, as many of you know, know very well. This is me talking very naively about representation theory, but do they have some representation theoretic meaning, or some meaning in whatever world you like to work in, that's not just superficially cluster theoretic, but says something about your world? Just want to really quickly talk about how this plays out in rank 2. If you have a finite or affine rank 2, then you can take a positive basis, and what you do is you take the G vectors for the transpose, and then if it's affine, you take the smallest integer vector in the limiting ray, and you've got a basis. That all works. In wild type, it's more interesting. If you're willing to take a field extension, right? Wild type is where you have this matrix with A and B off the diagonal, and you need A, B less than -4 to be in wild type. So if you're willing to extend your rational field to include square roots of -AB and square roots of -AB -4, then you could write a positive basis, because what you're going to do is you're going to put G vectors, you're going to take the G vectors, and you're also going to take a vector in each limiting ray. But those limiting rays are not rational, so you can't take integer vectors there. You'd have to have square roots, and then these particular square roots. If you're not willing to extend your field, if, for example, if you want to work over the integers, so it really feels more like cluster algebras of geometric type that you're used to, then you can take the G vectors for the B transpose, and then also you need to choose 2 vectors in the Badlands. I said well chosen in the slide, but well chosen just means it needs to be a basis for the integer lattice, and then but it has to consist of vectors that are in the 2 vectors that are in the Badlands, and that will give you universal coefficients. And also quickly, universal coefficients in the surfaces world. So these are basically the curves. If you're familiar with the surfaces model, there's these laminations that give you coefficients. The laminations are collections of curves. So the curves that are allowed to be in laminations, that's what I'll call an allowable curve. But I need to say what basically means here, because basically means, well, I want to change the definition of a lamination so that the non-closed allowable curves correspond to the tagged arcs. It's not quite like that in the usual definition of laminations. So let me just give a definition that shows sort of what the key idea is in the surfaces world. I want to tell you what a tangle is, and a tangle is just any collection of distinct allowable curves. And I think I'm going to rephrase Ippolito's question in this context. I don't need compatible allowable curves. They can cross each other and be completely incompatible, but I just take a bunch of them. I give them each integer weights, positive and negative. And I can compute, if I have a tangle, I can compute shear coordinates, because I can just compute shear coordinates of each allowable curve. And then I can take the weighted sum of those with those integer weights. Okay. A null tangle is a tangle where no matter what initial triangulation I take, initial tag triangulation I take, the weighted sum of shear coordinates is 0. Again, this is that familiar sort of, maybe familiar steaming kind of thing by now. That's what a null tangle is. And there's a little asterisk on every tag triangulation. If you want to take, a once punctured surface with no boundary components, then we need to do something a little different, but let's not get into that. So the null tangle property is this. It says for this surface, if a tangle is null, in other words, if it has shear coordinates 0 for every triangulation that I want to calculate shear coordinates with, then it must actually have all weights 0. So there's no non-trivial null tangles. And the null this theorem is basically just somehow about this independence property being the same in this context. The null tangle property holds for a surface if and only if the shear coordinates for allowable curves are a positive basis, and you can read universal geometric coefficients, but positive for the integers, for the over the integers basically. And there's a surprisingly short list of surfaces that are known to have the null tangle property. One is a disk with at most 2 punctures, an annulus with at most 1 puncture, a sphere with 3 boundary components and no punctures. The once punctured torus works, the 4 punctured sphere works. I have a student named Jesse Kofer who's hopefully going to prove that the dread torus has the null tangle property. That's the torus with 1 boundary component with having 1 marked point on it. And I should also acknowledge Barnard, Meehan, and Veal, some of my former students who work on the 4 punctured sphere. So that's just some of the some of the places, you know, some of the context on universal geometric coefficients in worlds where I like to live. And I should credit Veal. Veal has similar results for orbifolds, a similar theorem and similar list of orbifolds that have the null tangle property. So this is an okay time for questions if you have them. I am going to shift gears a little bit. So I guess this is good news. Sometimes in a talk, I feel like I need a new start. If you need a new start, now's the moment. And this will be a slightly different question that's not completely unrelated. But any questions before I go on?
You hear me?
Yeah.
When you write the real numbers, could you have just written the algebraic real number?
Maybe, but I don't think I think in a sophisticated enough manner to have really even considered that. Maybe, yes. I don't know. I don't know in general whether you get some I think you need all the real numbers. In fact, if you look at the once punctured torus, also known as Markov, the Markov, you know, quiver, I think you need all the real numbers as I think about it. Yeah, I think you do. Other questions? All right, so now we're just going to look at some G-vector fans. So here's an example of a G-vector fan. I was at Thomas's talk, and he put up an example of a G-vector fan and said that the very next example of a G-vector fan should be that one. And I was a smart aleck in the chat, said maybe the next example should be Markov, but that's probably a nice next example. And maybe a nice next example after that would be this. These are, you know, type A2, type B2, and type G2, if you like. But what I want you to notice about these examples is that to go from one to the other, I just put in more rays. In other words, I refined my fan, right, from one case to the other. And in fact, you could do this going into an infinite fan also, if you're willing to tack in that extra limiting ray, then you get refinement of fans here. And the refinement of fans just really means that to go to the finer fan, I'm breaking cones up into smaller pieces. But the thing to notice is that there's a relationship between the B matrices that corresponds to this refinement of fans. So here's another example. This is a B3 G-vector fan. And I'm going to superimpose on it an A3 G-vector fan with a similar sign pattern. And you'll see that there's this refinement relation. So the B3 fan, both of them together, and just the A3 fan. You're just really cutting cones into smaller pieces. And I should apologize for this. I'm so used to thinking of this picture that I just put it up without even thinking about it. But this is a stereographic projection. And even among co-authors, there could be different feelings about whether this is a good picture or not. But what I'm thinking about is a three-dimensional fan. And I want to be able to look at it in 2 dimensions. So I'm going to intersect it with a unit sphere about the origin. And then that will give me a decomposition of that 2-dimensional sphere. And I want to stereographically project that to the origin. So when you see a triangle here, for example, what you're really seeing is a fan with a triangle, sorry, a cone, an infinite cone with a triangular cross section. And so you're seeing this, but you're seeing this, this refinement relation. So here's a theorem. Well, actually, here's a definition, no theorem yet, but we're going to say that B dominates B prime if they're both n by n, and if every entry between B and B prime weakly agrees in sign. Okay, so maybe one of them is 0 and the other's positive, or maybe one of them is 0 and the other's negative, but other than that, we don't have one positive and one negative. So they weakly agree in sign. And also, the absolute values of entries in B are at least as big as the absolute values of entries in B prime. So as an example, B here dominates B prime. And the theorem is that if B is of acyclic of finite type and dominates B prime, then the G vector fan for B refines the G vector fan for B prime. And I wanted, actually you saw an example of this. We actually saw several examples, but here's the 3-dimensional example. And the examples, the finite examples on the previous slide were also examples. I think in the interest of time, I'm not going to say anything about the proof, but the proof is, except to say that the proof is about Cambrian fans and Cambrian lattices, and comes from the existence of nice lattice homomorphisms, which I think is really fun. Okay, I will also say that acyclicity matters. If I start with the B matrix on the left, which is, its quiver is an oriented cycle, and I take out one of the arrows, in other words, change a plus or minus 1 to zeros, I don't get a refinement relation. These are just two really different fans with the same number of maximal cones, for example, but no refinement relation. But let's think about what the consequence of this theorem is. What should we think of next if we have this fan refinement relation? What should we think of next? So here's just the theorem. The top thing is just the same theorem written again, this refinement relation. But first observation, if you have two fans and F1 refines F2, in other words, the cones in F1 are gotten by cutting up cones in F2. Well, F2 doesn't have any rays that don't stay rays in F1. In other words, every ray of F1, F2, every one-dimensional cone in F2 is still a one-dimensional cone in F1 because you can't get rid of rays by cutting cones further up. Okay, so that's the first observation. The second observation is if you're talking about the G-vector fan, then the rays, this is really just reviewing the definition in some sense, the rays of the G-vector fan are the G-vectors of cluster variables. And also, each G-vector is the shortest integer vector in its ray. So if we have an inclusion of rays, we have an inclusion of G-vectors. So the corollary to the theorem is that the set of G-vectors of cluster variables for B is contained in the set of G-vector vectors of cluster variables for B. Sorry, I said that without the prime. The set of G-vectors for cluster variables for B prime is contained in the set of G-vectors for cluster variables for B. And then, of course, if we're talking about G-vectors, we may as well talk about cluster variables. So there's an inclusion of the cluster variables for B prime into the cluster variables for B, and that inclusion preserves G-vectors. And so we would ask ourselves, does this have any algebraic significance? I mean, this is screaming out for a map, right? We should be mapping something, and does anything work? And the answer is yes. So here's a theorem. Suppose B is acyclic, same hypothesis that we've been saying. B is acyclic of finite type and dominates B prime. Then there's an injective G-vector preserving ring homomorphism from the principal coefficients cluster algebra for B prime to the principal coefficients cluster algebra for B, sending cluster variables to cluster variables. Now, I should say this is, you check this computationally for exceptional types, and then the other types are either surfaces or orbifolds. So I did surfaces, Shirabio, my former student, did orbifolds, and it all works. So the map, I think I'm going to go quickly over the map, but the point is, and actually I think in order to go quickly over the map, I will call your attention to really this and this. We're going to send initial cluster variables to initial cluster variables. And then there are these y hats that occur in cluster algebras 4. They're like coefficients times a product, times a monomial in the initial cluster variables. So we should send the initial cluster variables to the initial cluster variables, and we should send the y hats, the initial y hats, to the y hats times, and you need a polynomial in some, so the F polynomial is some cluster monomial. Basically, you choose this map in a way that makes the G vectors come out right. And then the proof is that this is going to be a G vector preserving homomorphism to something. You check injectivity using pretty standard tools, but then the thing that's hard and it seems to need, you need to think about it in each particular case is you need to check that it sends cluster variables to cluster variables. And like I said, we use surfaces, orbifolds, and computer to check that. And as a conclusion, since it sends cluster variables into cluster variables, it certainly maps into the other cluster algebra. So that's how that works. I think, again, an example would be in order here. So the very simplest rank 2 example has 4 cluster variables, 4 G vectors. And what I have in the left column is just the G vectors of cluster variables written as monomials in the initial, they're the exponent vectors on these initial cluster variables. And so this is the simplest. If we go one harder, there's one new G vector, this G vector 1 minus 1. But if you do this map, you're going to send the y, and these are f polynomials that I'm writing here. So I guess if you multiply these monomials in the x's times the corresponding f polynomial that I've written down, you get cluster variables. But this map where you send y hat to y hat and y hat, so y1 hat to y1 hat and y2 hat to y2 hat times 1 plus y1 hat. That y1 plus y1 hat is the f polynomial of the appropriate cluster monomial that makes this work, and then it works. Again, if you go one higher, you get one more G vector. And again, the same map works. Now, this is rank 2, and we're changing one number in the exchange matrix because there's not really much else you can do one step at a time. And so these maps will actually all look the same. If we go to one more level of complication, it's the same map, but it works. And so to me, even in this rank 2 case, this is somehow surprising that this should work. That somehow doing this map, everything will still, that you get a homomorphism this way, that everything should multiply together this way. But it does. And cluster variables map to cluster variables, and G vectors are preserved. So let me ask about your world here. What do refinement relations among G vector fans mean in your world? I mean, I don't know what G vector fans mean in your world, but the fact that there's refinement relations among them, what does it mean? Now, moving away from the fans to a consequence, what's the significance of an inclusion of cluster variables preserving G vectors in your world? So you have, this set of, you have objects that correspond to cluster variables. And if you do your construction with B and B prime, and there's a dominance relation, there's an inclusion relation among those. I mean, there's a sort of at least a map, an injective map from one set of those objects to the other. What does that mean? And the fact that that map preserves G vectors, what would that mean? Is an injective homomorphism of cluster algebra of the same rank meaningful in your world? Now, I know that there are people here who have thought about homomorphisms of cluster algebras, and there's a lot of great work on that. The thing that sort of still astounds me about the fact that these things exist is that it's the same rank. You're not losing a rank when you do a homomorphism, and you're not, it's really somehow the same dimension of things that are mapping into each other. So what does that mean? The fact that there's this injective homomorphism of cluster algebra, what would that mean in your world? And then really the question that's probably best to ask is, you have some construction that takes an exchange matrix as an input, or maybe you write it as a quiver, or however you do it. So if B dominates B prime, what's the relationship between your construction for B and your construction for B prime? Now, it might not be something that works in every case. The refinement relation doesn't work in every case, right? There's some cases that works and doesn't, but are there interesting cases where there's a relationship between those two constructions, really same construction with the two exchange matrices? Maybe you're doing, cluster categories, or, and so you do this. What's the relationship between those two categories? And maybe it has nothing to do with the questions that are above, like G vector fans, inclusions of cluster variables, and homomorphisms of algebras. But I think that's a question that I'd like to encourage you to ask. So maybe this is a good thing to go out on, just to say that, the world is bigger than acyclic finite type. And I've been telling you about these things happening in acyclic finite type. Two thoughts about that. One is that, for example, you might be in a skew-symmetric world. That might be where you mostly work, right? And so dominance relations among skew-symmetric matrices of finite type, there's not really a lot you can do. You can change a pair of plus or minus ones to a 0, right? That's it. But first of all, that might be more interesting than you think. And second of all, these things, which I like to call dominance phenomena, they're not limited to acyclic finite type. As I said before, they fail sometimes. Sometimes there's no good relationship. There's no, fan refinement relationship in the presence of a dominance relation among matrices. But there are lots of things that somehow don't seem like they should happen, that do happen outside of finite type also. So let me say a little bit about the fan refinement. So outside of finite type, we need something bigger than the G vector fan if we're going to talk about fan refinements, because the G vector fan isn't complete. Even that in that initial example, which I won't try to flip back to, where you were going from a finite G vector fan to the affine rank 2 G vector fan, you needed one more ray. You couldn't just take the G vector fan because it's missing that ray. And if you want to really do refinement relations, you can't just have that ray be gone, right? There's two fans that you might think about going to. One is the mutation fan, and this is where two vectors are in the same cone, if and only if when you compute the mutation map for them at every step, for every mutation map, they always are in the same domain of linearity, right? At every step, you're sort of doing one thing on one half of a coordinate hyperplane and something else on the other half of a coordinate hyperplane. They'll be, A and A prime will be in the same cone if you're always on the same side of that coordinate hyperplane at every step. And weakly the same, maybe one of them's on the coordinate hyperplane, that wouldn't hurt. Okay, so that's one kind of fan. The other kind of fan is, well, if you have a scattering diagram, it's made up of walls, right? Codimension 1 rational cones. In a way that can be made precise, those things cut up space into a fan. Okay, and if we start with the cluster scattering fan, sorry, the cluster scattering diagram in the sense of Gross, Hakenkiel, and Savage, then we get something called the scattering fan. Sorry, the cluster scattering fan of B. And in finite type, both of these agree with the G vector fan for B transpose. And so that's a place where one might think to look outside of finite type. In general, the scattering fan is finer than the mutation fan. Conjecturally, I conjecture that they're the same if and only if B is a finite mutation type. And we have a little bit of, Salvatore and I don't have this quite written up, but we've shown that works for affine type, and it's already just it's sort of almost by definition for finite type. So I'll stop on this slide. In many cases, the mutation fan refined the mutation. There's a refinement relation of mutation fans in the presence of a dominance. And I should have, sorry, the slide is missing. In many cases, when B dominates B prime, there is a mutation fan refinement relationship, and also a relation of cluster scattering fans. Not always the same cases, in fact, but this is known for acyclic finite type, some infinite rank 2 examples and non-examples, and also erasing edges cases. And also there's this notion of resection of surface and orbifold, the way of cutting apart a surface that gives you a dominance relation among exchange matrices where this works. So I won't go any further slides. I will say that that there's also interesting things happening with these ring homomorphisms between cluster algebras of the same rank in the presence of a dominance relation among matrices, exchange matrices that go beyond acyclic finite type. But I think I probably ought to stop here.
Thank you very much for this beautiful talk. Okay, are there any questions?
Hi, Nathan. Can you hear me?
Yes, I can.
Yeah, can you speak a little louder?
Okay. Let me speak louder. So for this refinement, okay. Can I talk about it from scattering diagram point of view? Like from the construction of consistent scattering diagram, the B2 you have square. It is like you decompose it into two walls, and then you give up adding the way. So I guess what you are hoping should be correct for any case, because
I'm sorry, it's becoming hard to understand. I don't know if you can stand closer to a microphone, or I'm sorry.
Guys are okay. No, I'm just saying, like in the construction of consistent scattering diagram,
Yes.
like the case is a square. Like you're thinking it, we can think it as decomposing the wall into two, and then we keep on adding the extra way to make it consistent. So that is why this refinement. Like from my entirely combinatorial point of view, that's how I would see your refinement, and that's why like the picture you have here. So I guess what you have should be true for acyclic case any, because that is the construction of consistent scattering diagram. Like for your, I don't. Yeah, I guess, just like a remark maybe.
Yeah, so the I guess if I understand right what you're saying, I mean, in the Grossack and Keelik-Savage, they show that the existence, they prove the existence by this recursive thing where they do it in every rank 2 situation, every rank, sort of around every codimension 2 thing until they're consistent. Yeah, that might work. I guess there might be a way to push that through, but I'm not sure exactly how I would write a proof down of that carefully. No, yeah, I think you're right though. There might be a way to approach it that way.
So the ring inclusion is how to frame it, but you can see it's like you just decompose the wall.
Right.
And so when you go from the smaller one to the bigger one, you just add back the decomposed.
Right. So I guess what I worry about in writing that down carefully is that you might be talking about some place that's far outside of the G vector fan. And so, in one construction, you're putting in some walls around a certain codimension one, some place where you're trying to make consistency locally. And for the other matrix, you're doing the same thing, but you need to know that there was a dominance relation somehow in the rank 2, there need to be you'd have to understand what the relationship was between exactly what you were doing in that spot. And that's, if it's out, for example, if it's outside the G vector fan, then I worry that, we don't really have control over what that looks like locally. I agree that what you're saying is very plausible, and I think that there might be an approach this way, but to me, the level of complication of trying to actually write this down seems very daunting. Maybe other people have more comfort with this construction and will be able to do it, which would be wonderful, I think.
This is just a follow-up question. For example, if you have a rank 2 matrix with entries B and minus C, and I'm not sure if I understand your dominance relation. Is that if B prime is bigger than B and C prime is bigger than C, so matrix with B prime and C prime, does that dominate the matrix with B and C?
If you put absolute values around those numbers, then yes. They need to keep the same sign pattern, and they need to, yes.
Yeah. Same sign for B and B prime, the same sign for C and C prime?
Yes, and then a difference in absolute values where the one exchange matrix has larger absolute values than the other, yes.
An expectation is that the fan of the larger one, the B prime, C prime one is a refinement of the fan of matrix of
So it's not an expectation. I'm trying to remember if I have the rank 2. I don't have the rank 2 sitting here. Sorry, so it's not an expectation because it works sometimes and it doesn't work sometimes. In rank 2, let me think about what I know. I'm trying to remember whether there's an exception to this already in rank 2. No, I think that was that was for homomorphisms. Yeah, so that, I think in rank 2, that should just work. You should have a refinement. Now you have to, I mean, in the cluster, so for the scattering fan, we're taking, every wall in the Badlands every rational ray in the Badlands is a ray of the scattering fan. It's a wall, right? So we need to include those. It doesn't work for mutation fans, which don't have all those cones.
Okay, thank you.
Polito, you have a question, you can go ahead and ask.
Yeah, I have a sort of, the question goes, okay, I have sort of a comment regarding refinement. Would it help you about coarsening? I think from a representation theory point of view is a bit more natural to consider coarsenings of these fans, because actually there is a dual to this G vector fan. When you have a finite dimensional algebra and you build this G vector fan, you have, this is dual to the lattice of torsion classes of your algebra,
yes,
right? And then, I mean, one needs to do the calculations, but then this coarsening actually would be a quotient of this lattice of torsion classes.
Yes.
And this is, I think it's completely, I mean.
In acyclic finite type, that's exactly what happens.
No, but okay, this is in general, actually, there is De Monet, Yama, Reading, Wrighton, and Thomas. They have shown that if you have a quotient of category of algebras, you have this nice quotient of lattices. And using the duality, so one can use maybe stability conditions and so on to see how actually this decomposes at the level of G vectors.
Mm-hmm. I'm worried about the fans case of that, because, for example, you could take a cycle, an oriented cycle, so that's type A3, and if you remove one arrow, then
Yes.
you don't get a refinement of fans. This is a case where
you do, I mean, because you need to consider also the finite dimensional algebra with the appropriate relations, right?
Right.
So if so in the case that I mean the three cycle itself doesn't tell you exactly the categorification. You need to add the potential, and in this case you would have a radical square 0, and then taking out one arrow would give you a refinement, because this long so the big root of A3 will not appear in this quotient algebra. So the 111 would not appear anywhere.
Yeah, so I've only formulated this in the sort of in the setting of exchange matrices, but it sounds like the quivers with potential setting is a good place to formulate this, and I think that would be interesting.
Yeah, and actually, I mean, and this is sort of some kind of folklore, I would say, that this is also beyond the quivers with potentials. Okay. Because the tau rigid, so the G vectors that you have in the exchange graph correspond to tau rigid objects, and these are completely determined. And these are two-term silting objects in some KB Proj. And if you start with a two-term silting and you quotient, or pre-silting and you quotient by an ideal, you can show that actually you would have a two-term silting pre-silting object in the quotient category. Now, if you started with something that is indecomposable, right, which was one of the guys that was giving you a G vector, in the quotient might not be indecomposable anymore, because maybe the map that you had between your two projectives does not exist anymore in the quotient that you are doing in the category, right? So in this case, actually, this point that was part of some wall at some point would be actually a sum of two G vectors, two or more G vectors. And this implies that this wall that you had, I say you were in a rank 2, this wall disappears, and then you are coarsening actually your fan and in a natural way, say, and it disappears exactly as the sum of a certain sum of the G vectors that you have surrounding this point in the space. If that makes sense.
To some extent, it makes sense. I think I would have to probably get back together with Hugh Thomas and Iyama to really have any hope of navigating those waters. But this is exactly why I wanted to give a talk like this, is because I think that there must be tools that people have in this group that could attack problems or generalize it in the appropriate way. Yeah.
Yeah.
Thank you.
Okay. Yeah.
Thank you, Hipólito. Are there any other questions?
Maybe I have a quick remark about the coefficient specialization. So, yeah, actually, I forgot what's your motivation for considering such specialization. Why you consider this?
I just found it an interesting structural question. I didn't have an application in mind for it, except that really the beginning of it for me was trying to understand section 12 of cluster algebras 4, where Fomin and Jolovinsky did universal coefficients, and realizing that, oh, in fact, the geometric coefficients are just the G vectors for B transpose. and then thinking about this problem, what should it be in general? Because, you know, for example, does it tell me how to make a fan that's bigger than the G vector fan? And then that was the mutation fan kind of came about in this project too. So it really was a very much a basic research motivation. I wanted to understand universal coefficients beyond finite type, and then universal geometric coefficients seem to be the place where one could do that.
So if I understand if I remember your definition of the specialization map correctly, so I think so, as you have mentioned, such specialization map actually they appear in the study of homomorphism between Cs for class algebras. And there was a one particular important family is that we consider something called twist automorphism, which exists for quantum groups. And also, if you check twist automorphism and Chamber answers something by Geisler and Schur, they do this, and there was really a repetition theory behind such kind of specialization map. So how you construct map actually it is determined by the repetition theory behind.
Mm-hmm.
And in general, so basically, so the application here is like you consider two seeds that share the same principal B matrix, but they have different coefficient part. And usually we consider such two kinds of seeds that they are mutation equivalent, but they are different seeds. And in this way, in somehow you get a twist, you get an automorphism of the cluster boson variety or whatever. So this is something twist automorphism. And in the application of Lie theory, it permute the canonical basis. So there are something. So I think for repetition theory, it is universal coefficient is. I don't know so much about that, but people often consider seeds which are equivalent, mutation equivalent, and consider specialization between them.
Mm-hmm. Yeah, I have a rule of not ever trying to think very hard when I'm in front of an audience, but I don't, off the top of my head, I don't know what would be the same and what would be different if we allowed ourselves to change also the initial exchange matrix. I think to me that's it feels like a very different problem, but I don't. But there might be some way that it all fits into one whole. I don't know.
Yeah, I think the situation actually fits in your definition. So basically, you start with one exchange matrix. You apply lots of mutations. You obtain another exchange matrix, but you require that the principal and frozen part are the same. Mm-hmm. This is only for these two seeds that you can construct this kind of interesting morphism between them, and which probably has a remutation theory meaning, like Dean twist or like the twist automorphism. They all appear like this.
I see. Okay. So you're saying you mutate
from one seed to another, such that they have the same unfrozen quiver, but the coefficient can be different.
I see. Yeah, that's right. That would, and if there were relationships between those, that would be interesting.
Yeah, like Dean twist is of course an example.
I see. Yes, I now see what you're saying. Yeah. There might be something interesting there to look at, yes.
Thank you. Are there any other questions, comments? I don't see any in the chat or in the room, so let's thank Nathan again.